Let's study with the new topic, shift registers. This is shift registers. What shift registers are? Shift registers are basically used to store a group of binary digits. That is, they normally store the digits in terms of single digit, and the number of flip-flops required to store the n-bit binary digit is always n. The shift registers are used to store the memory bit elements. They are actually the memory bit elements, and they store single bits like either 1 or 0s. And the more the number of bits, the more the number of flip-flops are required. So that is, if we have to store n-bit flip-flops, if we want to store n bits, n number of flip-flops are required. That is, to store n bit memory elements, n bits, we require n number of flip-flops. Shift registers are basically memory elements. They store bits and flip-flops. Normally shift registers use D flip-flops. These are very key criteria or key points about the shift registers, how they work. D flip-flops are used to store bits. Other flip-flops can also be used here, but the only important criteria is the flip-flops which are used to store the bits in them, they should always be in D modes. Now, shift registers have different modes of storing the data and different modes of extracting the data. So depending upon the different modes of input or different modes of extracting the data, that is, depending upon the input terminal and output terminal, they are classified into 4 types. They are of 4 types. 4 types depending upon input and output terminals. Let's take this as points so that it would be easy to recall all those things. The first type of shift registers are SI, called as serial input, serial output. Second type is SIPO, serial input, parallel output. Third type is PISO, that is parallel input, serial output. And fourth type is PIPO, which is parallel input, parallel output. Let's study each shift register step by step. So let's take the first one. First, SISO, that is serial input, serial output. Let us assume that we are trying here to store 4 bits. So assuming to store 4 bits, the circuit diagram for SISO is, as we have studied that serial input, serial output, or the shift registers required D flip-flops. That is, say D3, D2, D1, D0. Now since we have to store 4 bits, that is, if we have to store n bits, we require n flip-flops. So here we have to store 4 bits, so we require 4 flip-flops. That is flip-flop number 0, 1, 2, 3. This is Q3, this is Q2, this is Q1, this is Q0. the clocks. Clocks are applied externally to the circuit. Positive edge triggered clock pulses, as we can see. Let us say this is MSB, or the most significant bit, and this is LSB, the least significant bit. Now let us assume that we are trying to store 1010, these bits, storing these bits. So let's see how the clock pulses work and how the state of the flip-flops changes. What does shift register's function is? So let's take on with the clock. Input, 3 flip-flops, Q3, Q2, Q1, Q0. Say clock will be 0, 1, 2, 3, 4, 5, 6. Let's say. Let us initially work till 4th. Okay, let's start the clock pulses. Initial stage. This is initial stage where the clock pulse is not applied. Therefore, input is not applied. Let us assume that all the initial stage of the flip-flop is 0, 0, 0, 0. When the first clock pulse is applied, let us say when after applying for the first clock pulse, we give input as this bit first. So this will be first. Say this is applied. So the working will be this 0 moves here, this 0 shifts here, this 0 shifts to the next position, and this 0 shifts here. This 0 is out. Similarly, now during this second clock pulse, let's say this is the first clock pulse. Now the working of the second clock pulse. During second clock pulse, we try to store the second bit, which is this one. So if we give this one as the input 1, so during the second clock pulse, this one moves to Q3. Say 3, as say it is MSB. Okay, so this 0 moves here, this 0 moves here, this 0 moves here, and this is out. Similarly, during the third clock pulse, we try to store this 0, which is 0, so it moves here, this one here, this one here, this one here, and this 0, sorry, this 0 is out. Now it is this 0 is out. This will be the first stage, this will be the second, this will be the third. Now as we can see, we have still not got 1010. So, and still one bit is yet to be stored. So at the input of the fourth clock pulse, say this is third clock pulse, at the input of the fourth clock pulse, we have to store this bit. So we input this one, which is replaced by 1, this here, this shifts here, this shifts here, and this goes out. This is 0, this is 0. So the final output we can see, since we have to store 4 bits here, that is we store here 1010, 4 number of flip-flops required, and the final required output or the final number bits what we want to store 1011 has been successfully stored by fourth clock at the end of the fourth clock pulse. That is, the number of bits required is equal to the number of flip-flops is equal to number of the clock pulses, which is 1, 2, 3, 4. Okay, that is we have stored. So we can note down that to store n bits, we require first n number of flip-flops, second n clock pulses, Now let's check out how the number of clock pulses required to extract the bits. That is, we have stored the bits here serially. As we can see, it moves first here and then here and then here and then here. That is, output is serial. Similarly, let's check out the number of clock pulses required to take the output serially. Already we have this 0, so no need to extract, or no clock pulse required to extract this. So let's say we have to start removing, so we have to give a don't care input, which will be shifted here, this one here, this 0 here, this one here, and this is already out. Okay, so no need to calculate this. Now we give hash again, which will be this star here, 1 0, and finally again, which will go here, this will be here, here. That is, we can see to remove the bits we require n clock pulses, to store the bit, and here we took around 3 clock pulses, because while storing the fourth bit we already have got this out, so no need to calculate this clock pulse. So we can see this 3 are required, so we require 3 clock pulses, or we require 3 clocks to remove the bits. Therefore, we can summarize that for serial input, serial output, we require n number of flip-flops to store the bit, n number of clock pulses to store the bit, and n minus 1, that is n minus 1 clock pulses to remove the bits. So we can, in generalized term, we can write this 3 as n minus 1 clock pulses store the bit. Okay, sure.